Math 287, Quest College. I'm Joe Vasta, and we are covering section 2.3 on this video, and nothing yells out excitement more than the word terminology. Terminology for linear systems. Okay, it's not that bad, it's not as bad as it sounds, and it's a very short section, and I want to not use the word easy, but it's going to be pretty easy. So that is what we're doing. What is a linear system? Here's an example of a linear system. 2x plus 4y minus 2z equals 0. 3x plus 5y equals 1. So a few things you might not like about this is you might not like the fact that z is missing in this second equation. It's not really missing, it's there in spirit. It's plus 0z. And the other thing you might not like about this linear system is you might say, well, there are 3 variables, but there are only 2 equations, and that might upset you. You might say, well, I thought there were supposed to be 3 equations. No, this is legitimate. So let's write that down. There are 2 equations, and 3 unknowns, or 3 variables. We'll just say unknown since I already started writing this. So what this does is this gives us something known as a 2 by 3 system, where the 2 represents the equations and the 3 represents the variables. Okay, so we have these 2 equations, and this makes a system. And these equations happen to be in 3 space. These are, you can think of these as equations of planes. And this system, they're going to have things that are known as solutions, and some points in 3 space are not going to be solutions. So let's take a look at this. -3, 2, 1. Okay, so basically, you know, books might say verify if that is a solution, or verify that's a solution, or is this a solution? Let's see, how would you figure this out? Well, this right here is x. The second coordinate, so -3 is x, the second coordinate is y, and the third coordinate is z. So what you would do is you'd plug those in to both of the equations. So I'll do that right now. So let's see, this is going to be 2 times -3, which is -6, plus 4 times y, so 4 times 2 is 8, and then we have -2 times z, -2. This actually gives me 0. That one checks off. And the second one is -9 plus 10. This gives me 1. So this would mean that -3, 2, 1 is a solution. And I'll abbreviate solution there. Okay, what about this one right here? 0, 2, 4. Well, you're probably thinking psychology says he's going to say this one's not, because why would you do 2 in a row? But let's just check it. So I'm put 0 in for x, 2 in for y, and 4 in for z. So when I have that, I end up getting 0 plus 8, and then -2 times 4 -8. This equals 0. This is good. Now, if you're a government worker, you've worked for the government, you might say, oh, that's good enough. Yes, it's a solution, but we should check all of them. So let's see, 0, that's 3 times 0, and then we have plus 10 equals 1. So that's bad. So this guy right here, 0 to 4, is not a solution. And some of you are like, he's killing me, this is so boring. Well, you know what, if you're thinking that, let's do one more. Why? Because it's funny. It's funny when people are suffering. Or is it really? It's not really funny when people are suffering, but with math it can be that way. So check to see if that's a solution. Maybe you can pause the video. Okay, here it goes. I have 4 minus 4 plus 0, or you could say minus 0. This equals 0. Okay, that's a check. And then the next one is 6 minus 5 plus, well, there's nothing else, that equals 1. Wow, so what does that say? That says that 2, negative 1, 0 is a solution. Now, why did I put us through all this torture? I wanted to illustrate that a linear system could possibly have more than one solution. Okay, so that is what I want to say. Our system has more than one solution. Let's get out another piece of paper here. And I don't want to write this system down now, so we'll just go like this. And what I'm going to do with this system, okay, so this is great. We're going to learn how to solve these in this class. It's going to be one of the things we do. And I know some of you already know how to solve these, but we're going to be very efficient using matrices. So what we want to do is we want to rewrite this. We want to repackage it. Sometimes when someone buys an item from you, you make money off of them, and then you really ran out of ideas and you want to sell the same item, you just repackage it. And then the same suckers will buy the same item, but it's repackaged. And that's what we're going to do here. So what I'm going to do is I'm going to go ahead and take a look at the left-hand side of each equation, and I'm going to create a matrix by just putting the coefficients. So look, 2, 4, negative 2. 2, 4, negative 2. And so really, you know, the first column is going to represent the x's, the second column is going to represent the y's, and the third column the z's. Okay. Now the bottom row is going to be 3, 5, and then 0. Okay, so there is a matrix there. Now some of you might be going, well, what about the 0 and the 1? Well, we'll get to that. Okay, well, my variables in this equation are x, y, z. So watch this. I'm going to go ahead and put a column vector. It's going to have 3 components, x, y, z. So notice when you go ahead and do this matrix multiplication, we talked last time about the coyote and the roadrunner. Look, 2x plus 4y minus 2z. Look, that is exactly what that says. And this says 3x plus 5y. So this is going to equal, then you write down these numbers over here, 0, 1. And so this is matrix equality here, you know, equal, so we have 2x plus 4y minus 2z. This is going to equal the top part, which is 0, and that gives us our top equation. 3x plus 5y equals 1. So this is another way of repackaging this system right here. Okay, so this matrix has a name. Well, we like to call it letter A, and it's called the coefficient, and I'll abbreviate coefficient. This is the coefficient matrix. This matrix right here is a vector, so we're just going to write it as a bold X. It's kind of weird that we would use X and not Y or Z, and so there's bold X. Sometimes your book doesn't call it anything, but sometimes this is called the variable vector. But I won't mention it because your book doesn't have anything. And then over here, this one is lots of times is called, this is another column vector, vector B. And your book is going to call this the right hand side vector. I kind of think that's a dumb name because from time to time it could be on the other side, in which it's not the right hand side anymore. So some books will call this the system constants or the constant vector. Okay, so there it is. This is what your book calls them. Let us go ahead and look at the coefficient matrix. What is the size of the coefficient matrix? The size of the coefficient matrix is 2 by 3, which happens to also be the name of our system. It was two equations, 3 unknowns, 2 by 3 system, 2 by 3. That will always happen where the coefficient matrix will have the same numbers that we see up here when we're labeling the system. Okay, another thing that we want to introduce to you is this guy right here. So we have a, and then there it looks like an exponent, and the exponent, it's like that number sign or pound or hash or whatever. And so what this happens to be is a and then b. Now this right here is a concatenation. We're not multiplying those together. You wouldn't be able to multiply those together because this is 2 by 3 and this one's 2 by 1. This is a concatenation. And so I'm going to go ahead and write this out here. This is 2, 4, negative 2, 3, 5, 0. Okay, so there's matrix A, and then here is the right-hand side vector, which is 0, 1. So this thing right here has a name. It's called the Augmented Matrix. And this is going to help us when we solve these systems. And there are some teachers, maybe you'll see me do it, they'll put a line right there, because that will kind of tell you, you know, what the constants are, and it will help, because this kind of looks, this for me, when I've been working with these, it looks like 2x plus 4y minus 2z, and then this is like your equal sign, equals 0, and then 3x plus 5y equals 1. And so that is the augmented matrix. So let's take a look at our terminology here. The definition and theorem sheet is right here. AX equals B. Let that be an m by n linear system. A is called the coefficient matrix. B is called the right-hand side vector. And A, B, there's the concatenation. This is called the augmented matrix, and it is denoted by what we said here. So that's what we have here. Okay, so now notice something else about the linear system. Our linear system had infinitely many, well, it had, so I'm jumping the gun here, it had 2 solutions. So there is a theorem, so I guess I should have showed this theorem, that says the linear system, so just any linear system, has either no solution, exactly 1 solution, or infinitely many solutions. Okay, so you cannot have exactly 2 solutions. So on this one, when we have 2 solutions, this would imply, since we have a linear system, that this system is going to have infinitely many solutions. Now you may have remembered this theorem when it came to lines. Remember when you did systems of equations with just x's and y's? You had 2 lines that were parallel. That meant no solution. And then lots of times you would have a line here and a line here, and they would intersect at a point when you solve the system, and that is 1 solution. And then the one that, you know, people really are not big fans of when it just comes to just 2 lines is you have 1 line, and then the other line is on top of that 1 line. Okay, so the other line will be in orange, which means how many points do they have in common? Infinitely many points, and so this is infinite, and then I'll put an ly there, infinitely many solutions. So what the theorem says is that even if you have a higher system, when, you know, that has more variables, you'll still get no solution, 1 solution, infinitely many solutions. Now, infinitely many solutions is like what we have on our example, on this example right here. And you could just have 2 planes, and one of the planes, let's just say the plane's coming out at you, and it looks like that, and it's coming right towards you, and the other plane's doing the same thing. Let's say you walked around 3 space until you saw that. Well, it looks like they just have a point in common, but if they're coming out towards you, they actually intersect at a line, and that's infinitely many solutions. So infinitely many solutions is kind of dumb in 2 dimensions, but once you get 3 or higher dimensions, it actually becomes more interesting. Okay, let's take a look at our next definition here. So here is our system here. A system that has at least one solution is called consistent. A system that has no solution is called inconsistent. So our system, because it has at least one solution, so our system, for instance, so this system has infinitely many solutions, and from the definition, because it has at least one solution, it's called consistent. Okay. If b equals 0, so kind of going back to this, maybe we should look at this right here. If b equals 0, then the linear system is called homogeneous. Otherwise, it's called non-homogeneous. So is R, now it says b equals 0, but it's b equals the 0 vector, or the 0 matrix. Is R the 0 matrix? No, it's not. And you actually don't need that. You could just look at this right here and see that b does not equal zeros. If there's all zeros there, then it would be. So our system is called non-homogeneous. Okay. If x equals 0 is a solution to the linear system, then x equals 0, the 0 vector, is called the trivial solution. So do we have the solution 0, 0, 0, because that's when vector x would equal 0? No, because if you put zeros in the bottom, you get 0 equals 1. So our solution does not contain the trivial solution. The next definition, it says if the linear system is homogeneous, then it has the trivial solution. So think about this. If we had a homogeneous system here, that would mean that was 0 and that was 0. Then obviously, if you zeroed out all the variables, you would get 0 equals 0, 0 equals 0, and you would have the trivial solution of 0, 0. The last theorem says a homogeneous system can never be inconsistent. Why? Because from the theorem above, if it's a homogeneous system, then it has at least one solution, the trivial solution, which is 0, 0, 0, or whatever it is, okay, but the 0 vector. So that is what this terminology is. So we've finished all the definitions. I wanted to do one other thing here. Not that you have to memorize those definitions word for word, but our system, this is just an FYI, and this is getting pretty messy here. Our system has infinitely many solutions, and we just have 2 of them here. So I'm going to list all of the solutions, and you're probably going to think it's going to take me the rest of my life, but watch this. It is 1 minus 5t all over 3, comma, t, comma, 1 plus t over 3. And so that captures all the solutions, captures that one and that one. In fact, if t is 2, then you end up getting 1 minus 10, which is negative 9 over 3, which is negative 3, and then 2. And then 1 plus 2 is 3. 3 over 3 is 1. And it captures that one. And then this is the one where t is negative 1, and you can verify that. So we're going to learn in this class how, given us a system like this, how to find the solutions. And this, you might remember, if you had calculus 3, this is a parameterization of a line in 3 space. And so this line is where the 2 planes intersect. But not only that, but with parameterizations of lines, you can have infinitely many different ways of representing that line with a parameterization. So this is just one parameterization that captures all the solutions. So, you know, if you're kind of worried like, oh, should I know how to get that? No, not right now. You can actually plug these expressions in for x, y, z in each of these two equations and find that you get equalities. The t's go away and you will get equalities. Okay, so now let's go ahead and we're almost done with this section, by the way. We're going to do this problem right here, and you'll get problems like this in your book. So we had a linear system, and we wrote out matrix A and matrix B. We even wrote the augmented matrix. I'm going to go ahead and give you a problem like this, where they give you matrix A and matrix B, and we are to write out the system. So how are we to do this? Well, remember that this describes AX equals B. Okay? And remember, when I had the other matrix up, I wrote some variables above it. So my variables were like X, Y, Z. Oh, we ran out of alphabet, so I'll put a W there. So you could write this all out. I'll do that, okay? In fact, let's just do that. This is 1, 0, 2, 0, 3, 4, -5, 6, 0, 1, 0, 0. And so here are the variables, X, Y, Z, W. If you'd like to put the W first, then make sure, you know, don't switch it around within the problem, just be consistent about that. And this equals B, which is this, 7, 8, 9. So watch this, when you do matrix multiplication, the first part gives you an X plus a 2Z. So X plus 2Z equals what? It's going to equal the 7. The next one is 3X plus 4Y minus 5Z plus 6W equals 8. And the last one is, well, look at this. Everything's zeroed except Y. It's going to say Y equals 9. So in your homework, they'll ask you to write the linear system. Do we need to do all this? No, because you might be able to just kind of see it up here that X plus 2Z equals 7. You know, if you do a few of these, you will be able to just look at the problem and write out the answer. A caveat as well. Oh, wait, before we say the caveat, this is what kind of system? It is a 3 by 4 system, meaning that it has 3 equations and 4 unknowns. And that is actually the size of matrix A. It's 3 by 4. We did not write the augmented matrix for this one. We'll have practice doing that. And the caveat I wanted to say is the book uses x1, x2, x3, x4, and they'll use that right there. Now, I will use x1, x2, x3, x4, x5 when the variables are 5 or more. Okay, that's just a matter of style. Sometimes your book will just use x1, x2 when it's just 2 variables. But I'll use x, xy, xyz, xyzw, and then after that, that's where I draw the line. Then when I start going to the x1, x2, x3, x4, x5, when I get to 5 dimensions. So that is the end of 2.3. We don't have any applications that I'm going to show you, so keep up with your homework and have a good day. See you next time.